So it's still light outside, but somehow I feel like now we're entering, TASI after dark, where you've already gotten the knowledge as encoded in the lectures, and now it's trying to put some of these things into action. And two of our lecturers have agreed to give you tutorials where you, on your laptop, can actually do the things that you're learning about. So this week we have Christoph Weniger, who's going to be telling you about statistics, machine learning things, and really getting your hands dirty with that. And then in week 3, Stefan Höcke is going to talk you about Monte Carlo event generation. And in both of these cases, these are notebooks that you really can access, and you will be able to accomplish something over these tutorial sessions. But we decided not to completely overload you. And so weeks 2 and 4, where there might have been tutorial slots, is an opportunity for you as students to decide what you want. And maybe what you want to do is convince one of the other lecturers to do something on. That's also a valid thing. Or you might want to have your student talks during that time, or you might want to do volleyball or soccer or whatever. But we definitely wanted to give you a chance to get some hands-on experience with some of these, some of this material. And really grateful that Christoph has agreed to do this. Yes? Luckily, I'm going to hand the microphone over to someone who has all the answers, I hope. Starting off with, how do we download? Okay, excellent. So take it away.
Good, so now we start with this, with the first tutorial. Before I want to get there, I will explain a bit still about algorithms and elbow maximization. But if you can't wait, if you want to see the notebook link, go on Slack lecturers, the lecturers channel. I just added the link this morning. So it's a Google Colab link, a link to a Google Colab notebook. You don't have write access to it, so you have to copy it, obviously. I had troubles to use the GPU today, but you don't need a GPU for this. So everything is very much on the conceptual level. The networks are small. You can train this all on a CPU. Right, but if anybody has troubles finding that link, let me know. But I think quite a few of you already found it. And the plan today, so it's a bit experimental, is to simply let you go through the notebook. I will explain you a bit what this is about, and then we can see how it goes. And depending on how it goes, maybe somebody in front can say a bit about the results, or I could code up results. I think you can also use AI nowadays. So, and it's already there in this notebook thing. So I think each time when there is here, please add your answer, you can also click on use AI or something like this. I also wrote some of the code I wrote with GPT-4, so it was quite helpful. Anyway, so good. So before we go to the notebook, I still have to explain you the algorithm now that one has to run when optimizing elbow. So again, this is the evidence lower bound, right? So we have here an average, or we have here samples from the variational distribution that we want to fit. Just as a reminder, the goal is really to find a fit for this function such that it becomes similar to the posterior, right? So that's the underlying goal. And we, starting from that, using the KL divergence, which is also relative entropy, we arrived at this expression here. And in order to minimize or maximize this expression, we had to use the reparametrization trick, right? So instead of sampling from the distribution, we actually sample from some other parameters, and then we rescale and reparameter. Change those parameters through a function, underlying function, such that we in the end sample from Q. You will see this here. And on top of that, we also had to calculate the variational entropy. So the 3 terms that appear here are likelihood function, prior, and entropy. Good, so how does this look in the algorithm, which is already implemented in the notebook, so you can directly play with this? Well, the input for algorithm is you need, of course, first of all, a model, right? So for the likelihood function, so I didn't write this here. So you need a model for the likelihood function. And you need actually the log likelihood function and the log prior. And these need to be models that are differentiable. So in the example that you have, actually, there's a little code that simulates a ball that is thrown in a gravitational field. That code is fully differentiable because it's written in PyTorch. So that's your simulation model. And the prior is actually flat in this case, so it doesn't really contribute. Anyway, so these are the inputs. So you have a variational distribution, learning rate, training data. No, actually, that's not.
You lost the screen.
Yeah, it's my laptop went to sleep. So there's no training data in that case. So we have the likelihood function for a specific observation, and the prior, and then the algorithm works like this. So we first sample from this from a normal distribution, these epsilon parameters that we needed to reparameterize. So this is just sampled from a standard normal distribution. Then as a next type, we apply reparameterization. So we have our reparameterization function, which in the code is called reparameterize, which takes as input these samples that we just got, and also has internally some network parameters that you want to optimize. And so from this, we get actually the physical parameters that you're interested in. And then we plug those physical parameters, Z, we plug them into our likelihood model, and we plug them in our prior, and sum over all the examples in the mini batch that we have, right? So usually this will be like, I think in the code it's 64 examples. And on top of that, we need to calculate the entropy, but we wouldn't like Monte Carlo estimate the entropy. We can just usually calculate it analytically based on how this reparameterization model looks like. So we have a model for the entropy. And you see in the code, it's just a single line, which is the entropy of a normal distribution. And then after we have this elbow, we calculate the gradient. And actually, that's something that you don't really see. You just run autograd. And then you suddenly have the gradient buffers populated. So there's like autograd statement. And then we use the gradient to update the weights. And that's it. And then one can run this until convergence. In your case, you just run for a bunch of epochs until the loss function significantly decreased. So there's no much testing in terms of validation loss or whatever. So that's the algorithm. It has a lot of moving parts, right? And probably it's a bit confusing. But I think it's probably easiest to just get going and see how this looks in terms of Python code. And yeah, so is it there? Yeah, good. So let me explain you a bit. So okay, before I go there, are there questions about the algorithm? So I mean, there are two ways to compute the entropy, right? One would be to also Monte Carlo estimate it, so to just take like samples from this, plug it in here, then you get entropy samples. But in many cases, you can just calculate the entropy explicitly, right? So you just take that out and do actually the integral that this expectation value corresponds to. So if Q is a normal distribution, then the entropy is something that one can calculate analytically. Here we use a normal distribution. Actually, in the code, you use a very trivial normalizing flow with a bunch of affine transform. How's this called? Affine transform layers, I think. I will explain this tomorrow. But you see that actually your posterior looks nicer than a Gaussian, so it has some more complex shape. Which is good. But I will explain tomorrow how this works. But the fun thing is the way this is structured is that the entropy is still trivial to calculate because it just depends on the, so it's something that is easy to calculate. Good. Let me go through these examples. So there are three components. One is fitting a sine curve, then variational inference, and then variational autoencoders. And I have no idea how far you get. So you can just run the notebook once, and then everything is evaluated. Depending on how much you know about this already and your experience level with Python and so on, it will be quite fast or probably will take a lot of time, I don't know. But the first step is fitting a sine curve. I think I erased the results, great. So let me just run it, run all. Connect with our GPU. Good, so the idea is simply to do something that looks a bit like this universal approximation theorem. So there's just training data is simply drawn from a sine curve. And then we have a little multi-layer perceptron, which has one hidden layer. Well, no, it has two hidden layers, so it goes from 1 dimensions to n hidden dimensions, 64, and then to 64, and then it goes back to 1. And yeah, here it's trained. And everything is very explicit. So this here is the training loop. You can see that we here as loss function use the mean square error loss function. So that's here the criterion. And then at some point, you see the model evaluated. So the training data are the blue points. And the fitted curve from the multilayer perceptron is the red curve. And afterwards, your job, right, I also, I never did this before, but I thought it's fun. So I just show here the weights initially and then at the end. So for each weight, you can just collect all the weights from the network and show how they initially were distributed and then how they are in the end distributed. And the way, so depending on the network architecture and the way the training works, sometimes the weights change a lot or not. I'm not sure if I can learn much of it, but I thought it's nice to visualize the weights. So the weights internally will be typically of order 1 if you initialize the network, and some of them change a little, some of them can change a lot. Then the exercises are things like, okay, play around with the learning rate, see how this affects results, and maybe add a few layers or remove and see how this affects results, simply to get some intuition, because much of this is like reasonably simple theory, but whether something works or not is more often a practical question. And so it's good to see maybe, okay, if you use a learning rate of 1, probably the loss function immediately explodes. If you use it 10 to minus 5, nothing will change and so on. Right, then there's also some optional questions. Maybe you can skip them if you run through this initially. Then there's this variational inference part. For this, where is this? I wrote a little simulator that starts throwing balls from here with different angles and velocities. There's also wind, which is why this looks so funny, trajectories. GPT-4 came up with this sinusoidal wind model. I don't know, I kept it because. So, and then the balls end up somewhere here, and then the goal or the problem that we try to solve is, okay, let's assume we measured that after precisely 1 second, the position of the ball is 6, x equals 6, and y equals 1. So the position of the ball is here, with a measurement error of, I think I assume here 1, plus minus 1 meter in both directions. So that's a specific measurement, right, of the ball position after 1 second. And then one could ask, what's the posterior probability of initial launching trajectory? So in terms of velocity and in terms of angle. And if it works, then, right, so what to do? So one can then solve 2 problems. One is first to optimize, so to solve a maximum posterior estimation problem, and to simply basically fit the initial values of all these trajectories such that they all end up in the right spot. So this is like solving the elbow, but without the entropy term. Then you just get the best fit, and then all the trajectories will just converge to the same point. And if you read through the code, you will encounter all the concepts that we discussed. So differentiable simulation codes and trajectories that are fitting parameters and so on. And then at the end, the next step is then elbow maximization, where the goal is actually to, here in this case, find the posterior, assuming that the balls all end up at x equals 6, but y is unconstrained. And then the posterior samples look like this. So these are samples from the posterior for initial angles and velocities. And these are samples from Q. So we have here this variational posterior, right? So if we maximize elbow, blah, 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 then afterwards we will find a model for Q that looks like where if you generate random samples, they are distributed like this here. And you can think then about, okay, if I change the velocity, I have to adopt the angle in a specific way so that after 1 second, my ball ends up at exactly distance of 6, right? So if you increase the velocity, you also have to increase the angle so that it takes longer for the ball to end up at a distance of 6. Good, and then there are also some and then there are exercises related to this. So first understand where the elbow is in all this code mess. and try to figure out where these terms are and what I used as entropy. And then you can play a bit around with adding layers or removing layers and how much this changes the result. There's also something about variational autoencoders, which we can maybe do tomorrow. So, but if you can also go ahead. So variational autoencoders are models based on elbows as well, but without underlying physics model. So the idea is more to generate models in the first place. So you don't have physics models in that case. Good, so this is a very quick overview of the notebook. I suspect the easiest is if you just start, and I will go around and see how it goes. And if there are general questions or any questions, I mean, also raise your hand, come to me. It might make sense after a while if we go through some of the results together, although it's really not so much about getting results, concrete results, but more like playing a bit around with the code, seeing what is what, and trying to get some intuition. That said, are there questions already now, or problems, or any sort of things? Anything you would like to discuss? Okay, good. Then just get started. Any things I should so I guess if you are not too familiar or like super familiar with Python, much of the work is just understanding actually what the code does in the first place and what the functions, how the functions are defined and so on. But are there any specific things I could discuss right now?
I'm not familiar with Torch.
Yeah.
But with Python, yes. So
Yeah.
I can recognize that MLP is a class object, but I can understand, for example, sequential linear.
Okay, good. Yeah, these types of questions are great because then I can just, once the screen is there again. So sequential, linear, right. So this here is the definition of the, okay, I stand here. This is the definition of the neural network, okay? Just called LMAP here. The fact that it's NN module just means that PyTorch has some underlying mechanisms to keep track of what parameters are there and so on, because afterwards you want to have access to the parameters and their gradients. So the sequential thing, what this simply does, it's, if you remember when I was writing down this definition of a neural net, like T0 equals X, T1 equals blah, 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 T2, that's this here, just without the T1, T2, T3. So the input goes into this linear layer. The linear layer is an affine transformation from 1D to 64D. Then the output of this goes into a ReLU activation function. The output of that goes into a linear layer, which maps from 64 to 64. So that's another set of weights and bias. And then this goes again through a ReLU, and then a linear function that goes back to 1. So this is a neural network that would look like 1, and then 64, and then again 64. So these are 64 hidden nodes, and then it goes out again. Okay, so 1, 64, 64, 1, and with ReLU activation functions in between.
Just the matrix multiplication of the weight.
The linear thing is matrix multiplication and adding a bias. And so the input here is just defining the input dimensions. So input is, the first layer, it's one-dimensional because we just have X that goes in. Then it goes to 64. Then there's a ReLU activation function. So the little a, right? And then there's another matrix multiplication, now from 64 to 64. This goes through ReLU. And then this is again going back to 1D, essentially. And that's the network, right? And then the forward thing, it's called, this is just what is called when you call the network. It's called forward because it's opposite of backward. So it's like it's the forward pass of the network that you have to do before you can run the backward back propagation. Sorry, the screen switches off. So it's like the call function in Python when you have I think this just overrides call or is called from call. And this network essentially takes as input one-dimensional input and returns a one-dimensional output, except that there is then also batch dimension. So the input to the network would be batch dimension, comma 1. So this would be the input. Typically, these networks are written such that they can take many inputs at the same time and process them in parallel. So in this case here, it would take actually all the inputs from the sine function as input at the same time, processes it, and then returns something of that size again. Okay. More questions? Yeah.
So, when you change the learning rate, there is like a sweet spot where it works, right? My intuition tells me that the range, the set of learning rates that work should not be like separated. Like it should be like, let's say in this case, between 0.05 and 0.3. But is there a reason why, let's say, 2 to 3 doesn't work? Because let's say when I was playing with it, and I went to, let's say, 0.8, and it didn't work.
Yeah.
So I said, okay, why go higher? Is there a reason to expect that if I go higher, I could still get a good neural network?
No, usually the logic is, I'm not sure if there are exceptions to this, but usually the law, yeah, I don't have too many blackboards for this, but usually the logic is, I will just erase this. So okay, if you all played or if you start playing with the learning rate, what you will typically encounter is if you make the learning rate too large, the network just diverges and the loss becomes larger, and at some points it becomes infinite, and that's it. And the reason is somehow that if you run gradient descent, right, and you take a too large step, then you run pretty far outside of the minimum, and you hit some region which also will have a strong gradient. And then you might run even further, right? And then you bounce back, and you get further away from the minimum. So that's something that you generically observe. And there are automatized versions or ways of finding an optimal learning rate, which usually means you just keep increasing the learning rate to the point where it diverges the network, and then you make it a bit smaller. And that's then the point where you start. Because if you make the learning rate too small, initially it takes ages to get anywhere. Again, there's a lot of magic behind this. So there are also reasons to start small, then let it increase to the point where it almost explodes, and then let it decrease again. All of that usually is more or less empirical knowledge. So people have tried a lot of things, and there are certain set of things that work in practice and others that don't. Yep.
That part's okay. Now, why do we have this?
So would it be useful to also discuss this training loop, or is this less intransparent? So who would like to have a discussion of the training loop? Okay, that's enough. So yeah, you can just close your ears. So what you see here is the training loop, right? So we have a stochastic gradient descent minimizer. Usually you wouldn't use that. So nowadays, I think this is still the most popular minimizer is some version of Adam. And this are optimizers that actually adaptively change the learning rate depending on the weights that you are looking at. But stochastic gradient descent does exactly what we discussed. So it's a very simple algorithm and does its job. So you see here we set up the stochastic gradient descent algorithm. And as input, it gets the parameters, list of parameters from the model. So that's some PyTorch magic that happens automatically. It will just like know which parameters are there and need to be optimized. And you set the learning rate. And then there is also this mean square error loss function, which I could have written more explicitly. So maybe that's not so great, maybe. But essentially, it's just a function that takes two parameters, like the two parameters that you want to compare, data and model predictions, and calculates the mean square error loss. So like like it's essentially the chi-square function that I was writing at the beginning of the lecture. And then you see here model train. This just puts it in training mode. Doesn't matter too much for us. Optimizer 0 puts all the gradient buffers to 0. And then it calculates the output from the model. So that's the thing that is supposed to turn into a sine curve. And then it calculates here the criterion by comparing the target with the output of our model. That's just the mean square error loss. And then backward calculates the gradients. So it populates the gradient buffers, which were before all set to none. And I think there was a line somewhere where you can plot the gradient buffers. Where is this? No, maybe it's in the later piece of the code. But it's at the... Huh? For the up or down?
No, never mind.
OK. So you can actually look at the gradient buffers by just taking a variable which has a gradient, or for which you calculate gradients, and write .grad, and then you see what gradients are there. Anyway, and then optimizer simply goes through all the parameters here, checks, OK, there's a gradient buffer, I go in the opposite direction, and that's it. And the rest is just printing. And this thing here of actually showing the weights, that's optional. I just did this so that you can see the weights at the beginning and at the end. But that's the training loop. And this here is not really stochastic gradient descent, because each time the model sees all the training data is just the entire sine curve each time. So it's kind of gradient descent, but it worked. So because there are only 100 data points, there wasn't much point in making this stochastic. So what's the minimum number of hidden parameters that you found that still work? Maybe. No, I think one thing you can play with is the hidden parameters, right? I think I asked this here, so, and hidden. So what's the minimum number somebody found? 8? 16, yeah. So you can actually go to quite small numbers here, I think. But I shouldn't change this notebook now. Let me make a copy. Oh, God.
So I think, so this is 1, this is 2.
Yeah, I didn't add this really to the discussion. So usually, this is a very simple example just to see that you can actually get a flexible fit. But in the end, the typical strategy is you take your training data, or the data that you have available, and split it into training data, then typically validation data that helps you to determine when you're done with your fit, and then test data. And you evaluate the loss function on the test data. And see that that's a criterion for how well the model generalizes and applies to data that it hasn't seen before.
But like practically, now we have a final loss function.
Yeah.
So what do we consider a good fit with the final loss function?
You could imagine, for this example here, it's a bit boring because you have already like a very tight grid, right? What typical example would be you have only random samples along this curve, and then you're interested in whether the model actually predicts also between those samples the parameters correctly. So but it boils down to using data that the model that hasn't been relevant for the training, and calculate the loss function for that. There can be also other criteria, but that's like the most basic. Say it again.
Explain the like printed out without the trim.
This just shows the loss function.
Yeah, but
Yeah. Yeah.
We were wondering if there is any general rule, like a fixed number of, I
Yeah, I come to you in a second. So would it be, so who is actually looking into the variational inference result now? Who started with this? A few. So who is still thinking about the first example of just training a neural net for the sine curve? Maybe you already started also doing completely different things. So I'm wondering what would be the most useful thing. So one thing we could do is we could just collect questions, which I then discuss tomorrow, because I got a lot of questions in interesting directions, which I didn't address in the lecture, and I have tons of additional material I could talk about, but maybe it's more useful to talk about the questions that you have. So we could collect questions either now or via Slack, or I could talk a bit about this variation inference example. So any opinions, suggestions? Nothing really? Okay, so about the question part, I made a channel called, what is it? ML tutorial. So I would encourage everybody, maybe before we stop at 5, to spend 2 minutes to just dump random questions that you have there. Like, why are we doing this? What is this loss function? Why should we, how do we actually judge if it works well? Why does overparameterization work? Anything you can think of. And I try to come up with like answers to some of the most relevant questions until tomorrow, rather than just giving you more information about more abstract stuff. So that's point one. Then there's comment. The channel is already there. I think you should be able to join it. It's public. It's called ML. It's called ML tutorial. tutorials. I guess you can search it and then find it. Yeah, I'm not sure if I can just randomly add everybody. I guess that also doesn't work. So just go to that channel and add some questions. Everybody one question, okay? Then I have a lot to think about. Good. Otherwise, would it be useful to discuss now the variational inference example, or should we keep this for tomorrow? I could explain a bit what this actually does. Who would like to see that now? A few. Okay. Yeah, maybe I then. Is there anything else I should discuss? Yeah, so just wondering if there's something more urgent. Maybe not. Good. So if you look at this variational inference thing, well, this is essentially an example for the elbow maximization algorithm that we discussed today, right? And there was a question a few minutes ago, or a bit earlier in the tutorial, under what circumstances you actually would use an algorithm like this, right? So it looks a bit arbitrary, maybe, or a bit weird. So situations where you would use, so the most prominent example are variational autoencoders. So I guess many have heard at least the name. So these are generative models. I will discuss this maybe a bit more tomorrow. And elbow maximization is like what underlies their mathematical structure. So there it's very important. In the context of physics applications, the most interesting application that I have seen, or the most interesting applications I have seen are situations where actually the simulation model here, the physics simulation model, where you have some data that you want to model, or with your model parameter Z, where this itself also contains neural networks. So one example that the students that I was supervising worked on with the company was they wanted to model bridges, like how bridges vibrate, because then you can extrapolate when they crash. And so that's important information. And then you can model the structure functions of these bridges with neural nets because they are flexible. And so then suddenly you have a model that like models the vibration of a bridge, including neural network-based structure functions. And one can use algorithms like this to actually fit this then to data that you got from measuring how the bridge vibrates. That's nothing that you are doing here, but the underlying mechanism, I mean, you would do the same thing in order to fit the model. And the reason why elbow maximization is there interesting is because we actually care here about the gradient of the model, right? It looks like a bug that we have to calculate the gradient of the simulation model, but this allows then to optimize very high-dimensional problems where you have a lot of network weights, for instance. So there are these use cases, and there are also drawbacks of this algorithm, which I will discuss at some point. Typically, when you don't fit the posterior well, you underfit it. So typically, if it goes wrong badly in the sense that you underestimate your error bars, which is not a good thing if you want to get scientifically convincing results. So the failure mode of the framework is maybe incompatible with some science applications. But it's a very prominent framework that is useful to know. If you look at diffusion models also, so diffusion models are image generation models like DALL-E 3. You will encounter structures that are similar to elbow maximization. You have to think about KL divergences and all this stuff. So this reappears over and over again if you look into the machine learning literature, and it's good to get some intuition for that. Sorry, this was now just advertising why we do it. So now the example that I had here is simply this differentiable simulator that throws balls, right? And it's differentiable in the sense that if you know the final position, then you can calculate the gradient of that final position with respect to the initial parameters using backpropagation. Because the entire simulator is written in Torch, the same backpropagation that we use to optimize a neural net applies here to the problem of, okay, how does the final position change if I change the velocity or if I change the angle of the simulator? And that's the reason why the simulator is here written in Torch, right? So why would you write a simulator in Torch? Most people nowadays would probably use JAX to write simulators like this, but I'm not very familiar with JAX, although that's probably my fault. So I wrote it in Torch. Good, and you see the simulator basically, I mean, just solves numerically a very simple equation, iteratively, so there's no magic really going on. Right, and the interesting part, okay, so here these are just some examples for how the trajectories look like. What's interesting is, or what's critical in the end, is that here at this point, when we afterwards want to apply this framework, right, so elbow maximization, we actually have to treat the initial parameters, the velocity and the angle, as kind of network parameters. We want to optimize them. So this is why I initialize them here and set the gradients to true. So what this essentially does is it just makes sure that these parameters are not just parameters, but they are parameters with gradient buffers. So if you then run the simulator, put the output in a loss function, and run backprop, then the backpropagation will go all the way to these parameters and provide information about how to change them to minimize the loss. And right, so in this very first example, what you see here, and then, yeah, okay. In this first example, what you see here is the loss function that I use. Doesn't really care about the full trajectories, it just cares about the final position of each of the trajectories and compares it with the position which we measured, right? So the idea was, okay, we actually measured that after 1 second, the ball ends up at position 6,1, x equals 6, y equal 1, with some 1 sigma uncertainty. And the loss that you see here is simply that uncertainty. So it's the final position minus the actually measured final position in x direction and in y direction. And then I multiply it here with 0.5 because that's coming from the 1/2 from the normal distribution. In the normal distribution, you have e to the power 1, e to the power minus 1/2 difference of the parameters divided by variance square. Variance is 1, so that doesn't appear. And we have here just the 1/2. So this is the likelihood model here, right? So this is simply that likelihood function. And then the rest is simply optimizing the initial position. So the thing that we optimize here in this example, the elbow, but without the prior and without the entropy. So we just optimize that function. And we try to find the parameters for the initial velocity and the angle that maximize the likelihood. So it's really maximum likelihood estimation as an initial example. And that's what you see in the loss functions. The loss function just runs, simulates the trajectory, the trajectories for the specific initial values for the velocity and angles that we have, and it's actually 50 velocities and 50 angles, so 50 trajectories that are all simulated at once. And then the final positions are compared with the target positions. This gives us a loss function, so that's just minus log likelihood. And then we do a gradient update. And here the gradient update actually doesn't update any weights. It just updates the initial position, initial velocity and the initial angle of the 50 trajectories. And so if you run this for a while, what happens that all these initially randomly initialized trajectories, right? So this were initial velocities and angles just drawn randomly from some distribution that doesn't really matter, which led to random trajectories that look like this. They all these 50 initial values zoom together to one point. And to the same trajectory. So they all converged to the same answer, which is not a surprise because it's just solving the same problem 50 times. So that's, some sense, maximum likelihood estimation or map estimation if you have a flat prior. So this example here is the solution to this chi-square maximization problem that I was discussing in the beginning using gradient descent and the ability to propagate through a calculate gradients through a physics simulator. Now there are only a few minutes left, so I'm not going to talk about the second part, but the second part is essentially building on that example, and then rather than just trying the best fit value, trying to find a fitting function Q that allows you to throw the balls all such that they end up at distance of 6, right? So depending on the angle that you use, you have to use different velocities to end up at a distance of 6 after 1 second. And you see this gets learned, and then you get this nice posterior draws here. And we will discuss that part more tomorrow. So, right, questions about that?
Small question.
Yes.
So when I try to find the distance form, I get 2 trajectories.
Say it again. But so do you get 2 trajectories? Why do you get 2 trajectories?
Yeah.
What, you just were running the example? And
Yeah, I just changed the loss function to distance 1 from, I made the distance.
Yeah.
And from there, I just made it 1 away. When I run the same code, I get 2 of them.
yeah, I would have to think about this. So I will in a second. Okay, so I would suggest maybe add questions to the Slack channel. I think there are 0 questions right now. And we will continue with this tomorrow, and we will also discuss. And I really would like to address some of your questions that you actually have. So please put stuff into the notebook, and then in the Slack channel, and then we take it from there.